graphene systems themselves, take this Cartesian coordinate plane for example, are usually, as I'm aware, rather straightforward in and of themselves. This, for example, the XY Cartesian coordinate system, you got a unit of 1 this way, multiples thereof, unit of 1 this way, multiples thereof, at a 90-degree angle, linear algebra aside for the moment. The basic idea here of just that, perpendicular axes, XY coordinate plane, where you can specify any point just with a certain amount of distance along the x-axis, along with a certain amount of distance along the y-axis, and you have a point. Of course, the graphene system itself is rather straightforward. You learn about it in Algebra 1 in high school. That said, that doesn't mean that the functions, or the graphs of the functions that you graph within this Cartesian coordinate system are going to be straightforward, right, or simple. For example, the one here is rather more complex. Sure, you could have just a line going through, or even a circle could be considered much simpler than this thing. You can have much more complex graphs than even this. The point is, though, that the graphene system itself isn't complicated. It's the graphs that we're interested in within this rather straightforward graphene system. Take as another example here, we have the polar coordinates, where we have a certain amount of angle of turn, or argument, technically speaking. I'll just call it amount of turn or angle, and we have a certain amount of distance from the origin, and we get a point, right? So the magnitude, but I'll just call it distance. So we get a certain angle, certain amount of distance, and I'm not going to reteach here, polar coordinates. Feel free to review that on your own. Plenty of videos out there for that. But for our purposes here, just notice that we have a certain amount of angle, certain distance from the origin, and with those two things, r comma theta, what have you, we can specify any point within this plane. So the graphene system itself is rather straightforward, right? R comma theta. And yet the graphs we get out of this graphene system can be quite elaborate, quite beautiful, quite complicated. They can be simple too, but relatively speaking. Nonetheless, the graphene system itself is rather simplistic, even. Yeah. Same goes for the modular residue sequence graphene systems. It's the whole idea here, right? Since in turtle geometry you can, turn any amount, you can move a distance, any distance, at every given moment. You can do any turn, any distance, however you feel like it. So in order to get to the simplest, basic sense of what a turtle graphics system might be doing, a couple of things. I decided that, first of all, let's only have a unit of distance. No more of this. We can move however far we want. You're going to turn a certain amount, and you're going to move the same distance every time. Okay, so this is a unit of distance. And likewise, similarly, this sort of the simplest thing, arguably, that you might do with the angle of turn is limited to integral subdivisions of all the possible turns. So, for example, in this case, if our modulus is 2, then we only can go this way or that way. That's it. We can't go over here or over there or over here ever. Just 0 direction or the 1 direction. It's a little easier when we get to a less trivial case. Perhaps mod 3. We have our 0 direction, our 1 direction, and our 2 direction. These, 0, 1, and 2 being, of course, the least non-negative residues of mod 3. So we have these as our simplest sort of way to use vector graphics in this sort of modular residue sequence setting. So yeah, again, unit of distance, just this way, and that way, every single time. So let's take another look at mod 4. So mod 4, you have the least non-negative residues, of course, of 0, 1, 2, and 3. Those are the only possible values, at least non-negative residues. 0, 1, 2, and 3. There's no 0.5 or 1.5 or 2.75 or whatever else. It's just 0, 1, 2, and 3. Right? And so our robot, or cursor, or turtle, what have you, can only ever move in the direction of 0, 1, 2, or 3. Now, I want to make a little point on this, though. There are two different ways to implement this that are rather straightforward, obvious ways to do so, I would say. One is to keep it absolute, like, north, south, east, west. 0 is always this way, 1 is always that way, 3 is always this way, 2 is always that way. No matter where you are in this graphing system, you would always have 0 this way, 1 this way, 2 this way, 3 that way. And so if the next term is a 1, you go that way. Next term is a 2, you go this way. That kind of thing. That's what we call an absolute modular residue sequence graphing system, where the angles of turn are fixed, no matter which direction you are facing. Another way to implement this is what we call the relative modular residue sequence graphing systems, wherein, and this is a little more akin to the whole turtle graphics idea to begin with, wherein the angle of turn is based on which direction you happen to be facing after having moved about already. Right? So we start with 0 this way, we always start facing this way at 0. And so then if we have our first term is 0, we move that way. 1 unit, and that's it, we stop. Right? And then, so we're still facing this way, so if we get a 0 again, we would move that way. Now, on the other hand, if we instead, our first term is 1, then from the origin, right here, we would move a distance of 1 this way, but now notice we're facing this way, right? And so now for us, 0 is this way, right? Because now we're facing this way. Whichever direction you're facing is 0. And then it's basically left and right versus east and west, right? It's, now 1 would be this way, and 2 would be this way, and so on. I'll show you some easier to follow diagrams where those are all labeled. But the idea here is basically the absolute system is fixed, just like north, south, east, and west, whereas the relative system is more like your own personal left, right. Move this way, that to the left, move this way, that much to the right, that kind of thing. Turn to your left this much, turn to your right that much. That's the idea. So it's absolute versus relative. So of course we don't have to stop at mod 4. We can continue on to mod 5, because of course we would want to. And, so we still maintain, though, this unit of distance. That never changes. You can magnify it, you can decrease the size, but it's always the same size for each directed segment or localized vector. More on that in a bit. At any rate, always the same amount of distance traveled. And, we have now the residues, the least non-negative residues, mod 5, 0, 1, 2, 3, and 4. And so we're only ever going to turn one of these to one of these directions. And that's within either the absolute or the relative system. Absolute would always have 0 this way, 1 this way, 2 that way, and so on. Relative system would have your 0 facing whichever direction you are facing. All right, so if I'm facing this way, this is now my 0 direction in the relative, MRSGS. And so on down the line. This is what, mod 6. So we have these 6 different possible directions of travel. Mod 7, only these 7, and only ever these 7 in mod 7 MRSGSs, mod 8, mod 9, and so on. 10, 11, 12. Just like with other, uses of moduli in mathematics, we don't need to, per se, stop at any given modulus value. Of course, we have some limitations to consider when we're actually generating these in a computer. Accuracy and so on needs to be considered. However, theoretically, they don't need to stop. All right. So that's the idea of this first bit with these MRSGSs. All right. We have, again, a unit of distance. The simplest thing we could do is only ever have one amount that we can move, of distance, amount of distance. That never changes. And not only that, given us a mod 3, back here again, system, we can only ever turn in this direction, or face this direction, or this direction. So it's the simplest sort of possible scheme within this turtle graphics environment. Which again, usually you could turn however much you want. You can turn this way and move that way, this much, or that much, or this much, or that much. Anything goes, right, in your usual turtle graphics. So what we've done instead is limit the ideas, confine them to their simplest possible constraints. So only the same amount of distance every time, and only integral subdivisions of all the possible values of turn. In this case, 3 possible values, for example. Right, and then on to the next thing.